All right. Let's do this. All right. Hey, thank you all for hanging out. My name is Deian. I'm here to tell you a little bit of um, what it's like to write secure policies that can help you, for example, deploy the smart contracts that you thought you wrote and the ones that auditors actually audited instead of potentially buggy ones or potentially ones that have been backdoored by, I don't know, let's say an insider, which we've seen kind of happen more often than I would like. Um, Before I get started, I guess maybe I'll tell you a little bit about who I am. I'm one of the co-founders of Cubist. I'm also a faculty at UCSD where I co-lead the security and the programming languages groups. I also sometimes wear a board of directors hat at the Bytecode Alliance, which is kind of the organization that's been working on deploying and securing WebAssembly outside of the browser. A while back, I found a different company called Intrinsic that was working on Node.js security, maybe before all of Web3 kind of started doing a lot of stuff in Node that's really sensitive. Broadly, I work on secure systems. So like I've done a bunch of work that has landed in browsers, a bunch of work on secure hardware, so think like looking at hardware timing channels and things like that. But at Cubist, I've been working on our key management platform called CubeSigner. Now, the reason I guess like we started working on key management was largely because if you look at like what people are having a hard time with and where things go wrong, just purely by the amount of money that people have lost in the space has been largely a fraction of, a huge fraction, more than half of it has been due to key compromise or misusing keys. So it's a little bit hard for me to point here, but like the right half of this pie chart and a little bit into it is basically because of key compromise of one sort or another. And it's not always that people are losing funds. Sometimes they do silly things, like if you don't properly manage your keys, you might mint, $300 million worth of tokens that you don't actually have, which could actually have serious consequences if that's actually ever made it undetected. Now, the one thing that I want to kind of get at, like what's common between all these things is that all these things could actually be prevented if we slightly rethink how we do key management. From we just show up with a ledger to actually thinking a little bit beyond that. In particular, if you actually lock down your keys and secure hardware, and I'm thinking here server side, so that there's only one place where this key actually lives, then this means that we can actually have complete mediation. So we can have a policy that's sitting in front of this key that's in secure hardware that only allows us to sign transactions that are allowed by a particular policy. So we can actually enforce least privilege that would be hard to do otherwise. And of course, like this only like is meaningful if we actually lock down the policy itself. If I can just go to your system, modify the policy, well, I'm so glad that you spent your time writing this policy, but like if I could just modify it to do whatever I want, it's all bets are off, right? So like we really need to make sure that this thing is actually completely mediated, which means that our policy has to actually be locked down itself. So in a sense, we need kind of governance policies on policies, right? So like who's allowed to modify a policy? This is kind of like what we designed CubeSigner around. This is not really a product advertisement, but I think it's like a useful example of a thing that exists that does this, right? So like at a high level, like the thing just exposes an API for signing transactions, for creating keys, for managing users, so on and so forth. Then you have an authentication layer, which you need to make sure that, hey, who's actually trying to perform these actions, and a policy engine right behind that, right? So this is the thing that's actually going to enforce, am I allowed to sign this particular transaction or not? And finally, we have the secure hardware that does a bunch of fancy stuff by combining Nitro enclaves with HSMs, but the high-level bit is it's actually rooted in HSM, not just a Nitro enclave, and this is what gives us essentially this property that this is the only place that the key exists, and there is no weird protocol for somehow recovering keys. Like we have, like these things actually rooted in an HSM. Okay, so what does this mean at the end of the day if you had an architecture that looks like this? Well, it basically means things like the Bybit hack aren't a thing that we would have to necessarily be worried about. I'm not saying you shouldn't be worried about Lazarus, you should, but it does mean that a compromised UI doesn't mean a drained wallet, right? In particular, if we have our keys sitting server-side in secure hardware, we can ensure that these policies are enforced. So for example, we can ensure that 3 out of 3 YubiKeys are from the right users approving this transaction. We can ensure that only transactions to known warm wallet addresses are allowed, right? So like this is a simple policy that we can specify. We similarly can say like, hey, like maybe like these 3 people are actually rogue. Maybe we want to give the community more confidence in what these folks are trying to do, so we can have transfer limits, right? So we can say like, oh, you're only allowed to transfer, I don't know, $1 million over like a day instead of $1 billion at any point, right? So like actually having transfer limits is a thing that we can enforce, and we can ensure that this is the only thing that's actually allowed because, well, our keys server side, in front of that is this policy engine, and then we can have policies to ensure that those policies are actually enforced, right? So we can require, for example, maybe not 5 out of 3 UB keys, but let's say 5 out of 7 UB keys to change your policy. And in particular, we can have a policy that says like, hey, we can change this policy, but there should be a 7-day window before this takes effect. So you're not allowed to change the policy to something potentially malicious without somebody noticing for a week, right? So we can set these kinds of policies. Now, this is like something that you can do with other systems, right? And these are things that we have built in because they're common enough that you really want to actually have them. But like if we really think about like what is the key manager actually giving us and how should we be thinking about policies, where you can just say like, hey, Dan, we need this new policy. Can you guys please add it? We'll add it to the roadmap, and maybe we'll have a policy for this. Right, so like at the end of the day, like this has to be like important enough to enough customers that we're willing to do this. And this kind of sucks because this is a policy that you might only care about, and you might be the only person that cares about this because it's your particular system. And what this basically means is like, we should let you implement this policy yourself. So if you want to have a policy that maybe is not super common, I guess this one maybe is common enough, but I want to, for example, ensure that my developers can only deploy contracts and contract upgrades that have been built by our CI pipeline and can be that were approved by our auditors, whoever those auditors may be, right? This is like a particular policy, and like you could imagine adding something like this, but you can imagine having like way more complicated policies that are not generic across the ecosystem. And this is where like WASM comes in, right? So like in the previous picture, I showed you kind of like we have a policy engine with a bunch of those built-in things, but really the WASM policy engine is the thing that lets you do whatever you want, right? So if you can write code, you can express a policy, right? So you can do things like secure deployments, right? So we can say like the only thing you're allowed to deploy and the only contracts you're allowed to upgrade are things that were audited and built with our CI. You can do secure bridging, right? So we actually have customers doing this in production today, where basically they're watching one chain to see that, hey, you've, as a user, deposited funds here, right? So like and what that might mean is like I burned X tokens, and then I'm gonna release here on this other chain the corresponding X tokens because I saw that there was a corresponding burn here, right? So we can match the burn with a mint. You can even do this for Bitcoin. So like on Bitcoin, I could see that you've deposited 1 BTC, and I can mint 1 wrapped BTC of sorts on this other chain because I can actually point to a transaction on chain that this has happened, right? So like you can do things that you couldn't before, and you can extend to some degree these chains with custom logic that's specific to your application. In this case, that may be a bridge. And kind of we get the same security guarantees that you would get from running an actual protocol, like the safety properties, from the fact that these policies are running in a Nitro enclave, right? So we get the safety from the secure hardware. And then finally, you can do all kinds of other things if you're using a system like this. So you can do atomic cross-chain swaps. So for example, if both of us are using keys that are held here and we both have policies, we can ensure, for example, that I can only spend money as long as I've paid my debt, and vice versa. You can encode bi-party, tri-party agreements, things that are typically like legal contracts that you may actually want as code because you may want to have the invariant that your TVL is actually what you say it is, and you don't want to necessarily rely on a whale or a giant corporation that has a bunch of lawyers that may delay this invariant from actually being true for, let's say, a week, because like for that week, your protocol might just collapse, right? So we want to actually enforce these things with code. And you can do all kinds of other like clever things, and we have a bunch of folks that are actually doing this live as well, where you can have like essentially a private off-chain order book that you can match with like orders on chain, and you can implement things like a DEX with having like actual security guarantees instead of 3 trusted dudes. Okay, so there's all kinds of stuff you can do. What I'm going to talk to you about today is securely deploying contracts and upgrading these contracts. So we're going to look at some code, and you can interrupt me at any point, but basically this is a live demo. It's not a video or anything like that, so I'm just going to show you what this thing looks like, and then we're going to hit some road bumps along the way, and it's going to be fun. Okay, so on that note, I'm going to close off Keynote, and let's see if I can share my screen. Let's see. All right. There we go. All right. Okay. So here I have a key that I created earlier. I named the key contract upgrade because that's what we're going to do. It's just a secp key. We're going to run this locally. But one thing that I'm going to do, or maybe before I even show you that, is all those policies that I mentioned earlier. So you can have a multi-party policy that requires multiple people to approve the thing, and you can have a threshold. You can require YubiKeys. You can restrict IP addresses. You can set value limits, so on and so forth. Right? I'm gonna not set any of those policies because those aren't the ones that I think are interesting to talk about. The one that I will set is the multi-party approval for editing the policy itself. So this is the governance policy that basically says, hey, in order for you to change this policy, you need to be, in this particular case, D plus beta owner, and we're going to require me to use my YubiKey to approve changes to this particular policy. So anytime I want to change this policy, including the policy itself, I now need to show up with a YubiKey to change this policy. And one policy that we're going to set is a WASM policy. But before we do that, I guess I want to look at a simple smart contract. In this case, my smart contract is just a box that contains a value. There's nothing really interesting to it. And as usual, I'm going to have, let's say, a deployment script. In this case, the deployment script will just be a TypeScript script that uses a signer as you would anywhere else, right? So we're going to create a provider. We're going to create a signer. In this case, it's using a Cubist remote signer. And then we're going to deploy a proxy because we want to actually upgrade this contract later, right? And then we're just going to print out where this thing was deployed and what the proxy admin address was, right? And then when we upgrade the thing, we know that we're talking to the proxy admin and the new code that we want to deploy. Okay, so in order to deploy this thing, I'm going to npx hard hat compile. Let me make sure that you can all kind of see this. And this is going to compile a few of those contracts. Well, I guess. Okay. Nothing's changed because I compiled them earlier. I promise I'm not lying. I'm going to just show you and get the contract bytecode hash, because this is the thing that, if I was an auditor, what I would want from my auditors is basically for them to actually go through the process of building these contracts and giving me or recording the hash of the built thing, not just the hash of the source code where they audited this piece of code, right? So what we should be expecting from auditors, and sorry if a bunch of you are auditors, but we should actually be expecting them to build a thing and actually say, this is the hash that you should be deploying on chain, right? So in this particular case, the contract is OX51BE F1 and so forth. And then later we'll go through what that looks like for the upgrade. Okay, so in a separate tab, I'm going to just start a local hard hat node. And this is doing nothing really interesting other than we have a local network that we can play with so that we can deal with the network latency here. And the other thing I'm going to do in this other tab is I'm going to airdrop. And by this, I just mean we're going to basically send some funds from one of the keys local to hard hat to my key that's used for deploying this contract. In this case, this key is OXF5A, and if we go back here, it's the same address here, right? So it's OXF5A, is my address, right? So this is the key that we're going to use to do the deployment. I'm already logged into CubeSigner locally here. Here I have me as the developer, and then here I have me as the owner of the org. So these are two separate users. The idea is, as the owner, I'm going to set some config bits to let my developers do things, but not necessarily trust my developers to not be rogue necessarily, right? Like we've seen people deploy malicious contracts, in particular like layer 0 contracts, and then walk away with a lot of funds. Okay, so the airdrop function is not doing anything interesting. The next thing that we're going to do is actually set a policy that enforces, we want to make sure that we're only deploying approved contracts. So I'm going to show you a very simple piece of code. So this is the deploy policy, and I'm just going to go all the way to the top. So this policy will run before we sign anything if we attach the policy correctly to the key. So what it's going to do, it's going to parse the request. In this case, we're going to have an EVM request because we're working with EVM. We're then going to inspect the to value, and if it's not actually set to anything, we're saying like, hey, this policy is only, this key is only intended for contract deployments, right? So we're not going to let you call any contract or send any funds with this thing. The only thing that we're allowed to do is deploy contracts, right? The to field should be empty. Okay, so what does validate contract deployment actually do? Well, this is a very simple one. So it's not doing any of the fancy things that I mentioned earlier, but it is doing some checks. So the first thing that we're going to do is we're going to check that, hey, the key corresponds to this request, so that we know we're signing transactions that we can sign with this key, and we don't want to be confused into signing other transactions. And then what we're going to do is we're going to take the transaction data, and we're going to get the bytecode, right? So the data when you deploy a new contract is your contract bytecode. And then what I'm going to do here, just so that we can look at some logs, is we're going to print the contract address. And then, okay, great. Now we have the contract hash. What should we do with this? Well, if it's a proxy that we're deploying, we're going to say, like, this is okay. You could deploy the proxy. Otherwise, it's not the proxy that we're deploying. It's going to be the actual implementation. So we should make sure that this thing was actually approved by the auditors, right? And in particular here, is auditor approved, we want it to be this hash that the auditor should agree to. So we're going to like set a variable to make sure that that's actually the thing that the developer is allowed to deploy, but nothing else. And just to show you what this looks like, so for the isProxy primitive, this is just a function that checks like, hey, is this the standard proxy implementation? You could pass this as an argument instead, but I decided to bake it in because like I don't want to deploy anything else. I've picked my version of Hard Hat's, Open Zeppelin's proxy implementation, and that's the bytecode that we're going to use. And the auditor approved is a little different. So here, we are going to read from what we call a secrets config that contains basically the hash that the auditor has approved. Or in this particular case, it will be a list of hashes. So in our WASM policy engine, this is like one kind of API that you have access to. So you, as a user, you have the ability to read secrets, things like contract hashes, or API keys, for example, if you're making like HTTP requests, which we'll do a little bit later, right? But the idea is like you have a key value store, you have secrets manager, and you have HTTP endpoints from where you can write custom code. Okay, so here all we're doing is we're getting the string that I as the owner will set that will contain our contract hash, and then return true if the contract I'm trying to deploy corresponds to one of these things on the allowed list. On this side, as the owner, I'm going to actually set this environment variable or this secrets variable to this hash here. So I did this earlier, and this is roughly what it looks like. It's pretty straightforward, where we just say, set the policy secret, this particular key, to this list of contracts. So here, I'm just going to set this address here. Sorry, not address, this hash here, and this hash is the one that corresponds to the hash of our bytecode. So if it's not on this list, we shouldn't be like able to actually deploy it, right? So let's say as the auditor, what I said is actually here F instead of 6, because it's a different thing that we built, then we should see our policy fail. Okay, so this is the environment variable. As you can see here, I've set a few other ones earlier. I'll explain these a little bit later. Okay, so the next thing that we're going to do is actually set the policy on the key. Right, so the policy on the key, if we look at it, I've had an earlier policy here. You can do any of the other ones that I mentioned earlier, like transaction limits, receivers, and so on, but we're going to use our WASM policy engine. And so here, I'm going to do deploy /latest, and then here is where I'm going to show you how we're going to build this policy. So this here, we have this deploy RS, and then I'm going to build all my policies. I guess I built them earlier, and then because I've already attached, I've named this policy earlier. A thing already exists, but the thing that I'm doing here is I'm going to say like, hey, update the deploy policy. So that's the name of the policy with this new WASM bytecode. So I'm going to do this. It might take a little bit because we're sending this over. Oh, there we go. That was faster than expected. Okay, so what happened here is we deployed the WASM policy. Now this policy exists in the WASM engine. You should be able to run it. We can say, like, I want to use this policy by doing deploy /latest, or we can do version 14 because we want to pin down the exact version of the code that corresponds to the deploy implementation. Okay, so I'm going to do that right here, and I'm just going to clear my earlier DB. Okay, great. So now what we're going to do is we're going to actually run the deploy script. And this should now fail, right? Because the environment variable that we've set as the auditor or as the owner doesn't actually allow the thing that we're trying to deploy. So in fact, here we get a failed response that basically says, hey, like, this thing is not approved. And if we look at our policy code, where is this thing not allowed? Well, the auditor approved contract did not actually pass. Okay, so we can also look at the log for this thing, because this is, again, just code that's running. I'm going to get the logs for our particular piece of code and see, like, what did this thing actually print out. So it printed a bunch of things because I was playing with it earlier. But you can see kind of like what we're trying to do. We're checking this particular bytecode against what we've provided as the caller, as the thing trying to actually sign transactions. So, okay. Actually, in this particular case, I lied to you all. This is still running the old policy. That's why we're not seeing this generic error. So this is running the upgrade policy, which is failing, which is great, because I never actually approved changing the policy. So there we go. Like, I forgot to change the policy. It's running the old policy. I'm trying to deploy, and the thing is saying, like, nope, sorry. So if we look at this generic error, not policy approved, it's actually from this other policy. So I'm a rogue developer. This is what I would do. I would just try to, like, mess with you guys. Okay, so I'm going to veto this change, and then I'll show you what it's like to run the actual thing. Oh, all right. Let me tap this thing. Great. Okay, so this part was real. I did deploy the thing. The part that I never actually successfully did was update the policy. So let me do that. And here, I'm just going to say deploy /v14, or you know what, latest is fine for the demo. Okay, so this succeeded, but now as the admin, I need to actually approve this thing. And if we look at what we're changing the policy to, we're changing it from whatever it was before, which was our upgrade policy, that's what the name resolves to deploy /latest. Okay, so I'm going to approve this policy edit, and as the owner, I can say this is a cool thing for us to do. Okay. Done. All right. So now the policy is actually set to the deploy policy, let's actually deploy the thing. And now we should fail because, again, the auditor hash is different, right? So unrecognized contract bytecode is what we're failing with, and this is in deployed RS. So we basically end up failing over here because it was not a proxy and it was not the auditor-approved thing, right? Remember, like what I did over here as the auditor is I changed that 6 to an F. And let me just confirm that that was indeed a 6. Oh. Yes, it was a 6. OK, so I'm going to change it now to the actual thing. OK, great. And I'm just going to kill my node to make my life easier here. And now, as the not rogue person, run the airdrop and then run the deploy. So now we should be deploying successfully because our policy says, hey, this was, like we're deploying a few contracts, right? In particular, we're deploying the proxy and we're deploying the actual implementation, right? So in this particular case, it succeeded. We now have a contract address. This is my contract address here. We have our proxy admin here. We're good to go. Yeah? OK. Any questions so far? No. All right. So what we're going to do next is we're going to update this piece of code. So the way we're going to do that is we're going to look at our upgrade script, which, why don't we take a slightly different one here, is we're going to take box evil, which is just a different contract from the one I, as the auditor, would approve, right? So this is just another contract. As the attacker, I might want to deploy this thing instead of the other thing. Maybe it would be a tweak to the box v2. Doesn't really matter. But the idea is we're going to use hard hat off the shelf, nothing interesting here, and we're just going to say like, hey, please upgrade my box contract to box evil. OK? All right, excellent. And now, after I've kind of deployed the thing as the actual org owner, I would have changed the policy from the deploy policy to an upgrade policy. You can imagine doing all as one gigantic policy, but for a demo, it's easier to do one instead of the other. OK, so here I'm going to change this to upgrade latest. And again, I'm going to have to approve the change from the latest, that was the deployment, to upgrade the latest. All right. And there we go. OK. So now our policy has changed to the upgrade policy. Now, what does that policy look like? Well, this one is a little bit more complicated, right? So in particular, this is the one that we're going to tie back to our CI pipeline. So I'm going to go to the top and walk you through exactly what this is doing. So here we have two cases that we match on, which is the two, if 2 is actually set to something and if it's not. So if it's not set to anything, again, this is just a contract deployment. As part of our upgrade, we are actually going to deploy a new contract, right? So we're going to want to make sure that the contract that we're deploying is something that was, again, approved by an auditor. And we're also going to make sure that this was actually built by our CI instead of just me on my local machine. And then separately, we're going to call the proxy admin to actually make the change, right? So we want to say, like, don't use the old contract, use the new contract. So we want to make sure that we're actually allowing the change to the new contract, not just allowing you to deploy the thing. But this is basically a two-piece thing that's going to happen. Underneath the hood, this is what hard hat ends up doing. So it ends up deploying the thing, and then it's going to call upgrade and call. So validate contract deployment is going to look similar to what we looked at before, but a little bit more involved. So we do the same thing where we check, like, hey, what is the bytecode of this particular contract we're trying to deploy? But here, I'm also actually getting the nonce from the request because we want to compute what the new contract address will actually be. Right? So that's the thing that we're going to then tell the second step, hey, you're allowed to change the contract to this new thing, and this new thing is this contract address that we're storing locally in the database. OK, so we're going to compute the nonce, or we're going to get the nonce from the transaction. We also get the sender from the transaction. and we get the bytecode from the transaction. Then we check, as we did before, was this auditor approved? So we're going to need to add this new contract to our list of approved contracts. And then what I'm going to do here is actually check against GitHub that this particular hash, so this is the hash of the bytecode, was actually checked into the repo. Right? So we're going to use GitHub's attestations to actually verify that this went through our CI pipeline, ideally was reviewed by a bunch of people, potentially even auditors, they thumbs up, and then the build system itself built that bytecode and agrees with what I'm trying to do here as a developer. And then finally, after we're done with that, we're storing the address. So the get contract address here is just a function call to the Ether's implementation that computes the address from the sender and the nonce. And this will be our new contract that we deployed. And then later, we're going to use it in our validate proxy upgrade to make sure that that's the only thing that we're allowed to call the proxy admin with. So this is what this does. So this basically checks that the to destination is the proxy admin. This is a thing we're going to use, again, the environments or secrets variables to set. And we're going to get the new contract address from the transaction and make sure that thing actually is the thing that we stored in the database earlier. So this is what the fetch deployed does. It fetches that address. So if you look at get new contract address, this is taking our request, right? So this is the proxy call. It's computing the selector for the function that we're going to call here, which is upgrade and call. So we could have baked these in as fixed things, but instead we could just use libraries and write natural code. Then we're going to take the data from the transaction, take the selector, and make sure that the selector matches upgrade and call. And then later, we're going to check that the input that we're calling it with is actually the address of the contract that we just deployed. Right? So this is the thing that makes sure end-to-end that, A, we've deployed a contract whose bytecode is in our CI pipeline and approved by an auditor. And when we're calling this function upgrade and call, we're calling it with that address instead of some other potentially bogus address. Because if we hijack this would have been just as bad. Okay, are we all on the same page? Okay, excellent. So now what we're going to do is we're going to just run the upgrade. Well, I guess before I do that, let me approve box v2. So this is the thing that I, as the auditor, will approve here. Excuse me. Okay, great. And then we're going to run the upgrade script. Okay, so this failed. Why did it fail? Well, we don't have a GitHub attestation. And if we're trying to figure out, okay, what are we trying to find an attestation for? Well, we can look at our logs. And this will tell us, hey, we're fetching attestations for this thing, 5C, blah, blah, blah. That's actually not our V2. That's our evil contract. Or it should be. And indeed it is, right? So we roguely tried to deploy this thing. This thing was never made it through CI. Even if it did, let's say the developers colluded to actually deploy this piece of code, right? And so one way you can do that as a developer, right, is we can look at our workflow, and instead of just publishing here the box v2 bytecode, we could publish the box evil bytecode hash instead, right? So if you're all malicious, you can compromise your CI pipeline this way. But at the very least, we should here have some separation with the auditors who have said that, hey, the thing that's on the allow list are just these two pieces of code, right? So this address here corresponds to our box v2, not our box evil. So as long as one of those things says this is the actual contract that you're allowed to deploy, then we should be good. Okay, so I'm going to modify the upgrade script here to deploy v2 here. And now, it succeeded, right? So what happened? Well, it passed all the checks that we had here, which are the for the contract deployment is that this thing was actually audit approved, and that there's a GitHub attestation corresponding to this particular contract. Okay, so how do you know about the GitHub attestations? Well, here is actually something that I did a little bit earlier, just to be on time for this, is I published that particular piece of code, right? So here is the workflow that we saw earlier. As part of this workflow, we have an attestation. This is the attestation that was actually looked up, and these are the artifacts corresponding to that thing. So I could just delete this. Let's see, delete all logs. Maybe this will do. I'm not sure if that will delete our attestation. I don't think it would, but let's see. Okay. So if I'm going to rerun everything. Deploy. And here, I'm just going to deploy latest. Just so you don't see that I'm making any of this up. Okay. So we're going to deploy again. And then we're going to... I did not airdrop. All right, there we go. And in the meantime, I'm going to start updating my other policy to upgrade latest. Okay. Excellent. Okay. And lastly, let's run the upgrade script. Great. One second. Oh, I forgot to clear my database earlier. So it's only allowing me to deploy the thing that I've previously deployed. Okay. Okay, great. So I guess the attestation stays alive forever. I guess the only other bit that I could show you is modifying the thing and publishing an evil thing won't work if we remove the, again, tweak this 1 to an, let's say, an 8. So that the auditor is the one that says, like, hey, this is actually a different thing that we're approving, but you've already seen what that looks like, so there's no point in me going through it in a lot of detail. The only thing that I want to kind of like maybe hone in on as the last bit is, this is just normal code that you would write anywhere else, right? It's not like weird smart contract code. This is code that is doing things like making network requests to GitHub and fetching these attestations, right? So like this is just using, if we look at the definition for fetch attestations, at the top here, we can see like what crates can we use? Well, we can use pretty much anything that compiles to WASM from the Rust ecosystem, right? As long as like obviously like we trust these things. But we can use Serde for serialization, deserialization, and from our side we have the GH tokens that we've again kind of encoded as secrets that you pass to the WASM policy, so that when we make this request here, we're including things like the auth header that includes my secret private attestation token, private access token, so whatever GitHub's PAT stands for, that I've earlier included as a secret here. So here you can't actually read the secret because it's actually encrypted directly to the enclave. You can set it again to a newly generated thing, but the idea is you can encode secrets like this and make potentially secret requests to fetch data that is not public. And again, you just write code as you usually would. So I guess on that note, I think I will stop here and just reiterate, this is like, to me, a pretty interesting use case because it's one that we've had customers come to us. We're like, hey, we've had developers that have deployed contracts that are malicious. Can you help us somehow deal with this? And this is one way you can do it is well, I can help you, but you can also write code like this that checks the deployments against what you've built, and also whatever protocol you may have with an auditor. So if you can have auditors plug into the system, that works pretty well. So instead of having an environment variable here the way we did, you could imagine instead making an HTTP request to an auditor hub where you have the list of contracts that were approved by this particular auditor, and now you kind of have an end-to-end system without necessarily any of this manual stuff that I've used here for the demo. And on that note, I guess I'm happy to take any questions or give you back your time. All right. Thank you all.